Yes. Yeah. So does everyone have the collab open, ready to go? Okay. And for those who just came here, it's in the workshops channel in the Discord. Mm. So I'll go ahead and get started. Let me go. So welcome to the workshop. This is going to be an introduction to convolutional neural networks and transfer learning. And yeah. So image data is represented as a 2D grid of pixels, where each pixel corresponds to one or more values. So if you look at the image 2, we can assume that it's represented as a matrix, where each pixel of this image has a corresponding entry in the matrix. And previously, images were treated as vectors and were flattened to 1D vectors in order to feed them to a fully connected MLP, but this method disregards the spatial relation between pixels. So convolutional neural networks were introduced to take advantage of the fact that nearby pixels are typically related to each other. So let's imagine that we want to detect an object in an image. The method that we use should not be concerned with the precise location of the object in the image. So cats usually don't fly. However, we do want to recognize a cat if it were to appear at the top of an image. So we define a few principles to express this intuition. The first one is that the network should respond similarly to the same patch, regardless of where it appears in the image. And this principle is called translation equivariance. And only a small neighborhood of pixels will be used to compute the corresponding hidden representations. And this principle is called the locality principle. And eventually, these local representations can be aggregated to make predictions at the whole image level. And as we proceed, deeper layers should be able to capture longer range features of the image in a way that's similar to higher level vision in nature. Okay, so with those principles in mind, let's talk about convolutions for images. In convolutional layers, an input tensor and a kernel tensor are combined to produce an output tensor through a cross-correlation operation. And the input is fixed by the user, and we learn the kernel weights. In the 2D cross-correlation operation, we begin with the convolution window positioned at the upper left corner, which is shaded in blue in this picture, of the input tensor, and we slide it across the input tensor, so marked in green in the second image, both from left to right and then from top to bottom. When the convolution window slides to a certain position, the input subtensor contained in that window and the kernel tensor are multiplied element-wise, and the resulting tensor is summed up, giving out a single scalar value. This result gives the value of the output tensor at the corresponding location. So if we look at the blue part of the input, we first multiply 0 with 0, and then multiply 1 with the corresponding value in the kernel, which is also 1. And then we move to the second row and multiply 3 with the first value in the second row of the kernel, which is 2. And then we finally multiply 4 times 3. And then we sum up all of these values to get 19. And then now we shift our convolution window to the right, which is highlighted in green in the second image. And then we repeat the same process of multiplying and then summing up. So let us take a look at this process in code. So let's just first like run the first two things, which is just like installing and like importing like stuff that we need. So if everyone can like follow along when I'm running, that would be good. And let me know when everyone's like done running both of those. Does anyone have any questions so far? Like anything you think you didn't understand or anything you want me to like go over again? Okay, I'll continue on if like everyone's like good to go. Okay. Um, okay, so we implement the process that we just discussed in the function below, which accepts an input tensor x and a kernel tensor k, and it returns an output tensor y. So what we're doing here is we first initialize y with like all zeros, and then we iterate over like y. And each entry of y, we get the input subtensor, which is the part of x that we want to focus on, like the convolution window. And then we multiply that with the kernel k. And then we finally sum it up. So we do that for every entry in y, and that's how y gets populated. So let's run that. And then and now we can construct the input tensor x and the kernel tensor k to validate the output of the implementation of our function of the 2D cross correlation operation. We can use the example of the image that I showed earlier. I think it is like the image earlier. We're going to implement that. So we have the values for x, the values for k, and we call the function. And then if we run it, we see we get 19, 25, 37, 43, which is what we have in the image over here.
Why is it x dot shape 0 minus h plus 1? Like the dimension. Oh, is that the dimensions of like the output?
Yeah.
Okay. And what's the reason you add 1?
Just taking a look. Um,
So the height and width is the kernel, right? So
Mhm.
HW, we're going over shape, let's say it's 7, we have a kernel of 4. So if we overlap or if we go through the entire thing, we will basically have to just bias it by 1 in order to get the total output, right? So let's say 7 minus 3 gives us 4, but the total number of steps that we will take over the image are 5.
0, 2. Yeah.
So, or maybe getting it off slightly. Wait, let me think.
I think if you open the slide again, you'll like understand better visually.
Yeah,
It's fine. Okay.
yeah, that's a good way of looking at it. So,
So in this case, it would be 3 minus 2 plus 1.
yeah,
Yeah.
because the total number of steps would be, yeah, the overlap.
Mhm. Okay, thanks.
Okay. So now we can implement a 2D convolutional layer based off the function that we defined above. In the constructor, we declare weight and the bias as the two model parameters. And then the forward propagation method calls the function and adds the bias. So here we initialize the weight and the bias, and then we call the function in the forward propagation method. Please run this. So now let's look at a simple application of the convolutional layer, which is detecting the edge of an object in an image by finding the location where the pixels change. So first, we construct an image of 6 by 8 pixels. And over here, the 4 columns in the middle are like black, which is denoted by the number 0. And the rest of the columns are white, which is denoted by the number 1. So let's just assume that this is an image. Um, And now we construct a kernel with a height of 1 and a width of 2. And then now when we perform the cross correlation operation, If the horizontally adjacent elements are the same, the output will be 0. Otherwise, the output will be non-zero. So, yeah. So we see that we detect 1 for the edge from white to black and -1 for the edge from black to white. So if we go up here, the edge from 1 to 0 is, I guess, like the second edge. And then in our matrix over here, that's all detected as 1. So it has detected that there is an edge. And then over here, we see like the second edge from the end is 0 to 1, and that's being detected here as -1. And then we can now also apply the kernel to the transposed image, and this would be the transposed image. Just like flip the matrix. And then if we call the function on that, we see that we get all zeros. So the kernel only detects vertical edges. It does not work for horizontal edges. Yeah. Okay. So now let's try to learn the kernel that generated y from x by looking only at the input-output pairs. So first, we'll construct a convolutional layer and initialize its kernel over here. And then in the loop over here, we get the squared error, and then we compare. So we do that by subtracting the output y from the predicted output y hat, and then we square that. And then we can then calculate the gradient using backpropagation and update the kernel using gradient descent. And if you all weren't here for the last workshop, gradient descent is the process of minimizing our loss or error by updating the weights and biases in our model, like iteratively. So now if we run this, we can see like the loss has like dropped to like a really small amount after 10 iterations. And then if we look at the kernel tensor, it's pretty close to like the tensor that we defined earlier, which was 1, -1. And then we get over here pretty close, 1.01 and -0.9. Okay. So let me go back here. Okay. So a feature map. So the convolutional layer output, so like the pink matrix, I guess, is sometimes called a feature map, as it can be regarded as a learned representation in the spatial dimensions to the subsequent layer. And then now let's talk about padding. So after applying many successive convolutions, we end up with outputs that are smaller than our input. That is, we tend to lose pixels that are on the perimeter of our image. So say we start with like a 240 by 240 pixel image, and then we have 10 layers of 5 by 5 convolutions. That would reduce the image to 200 by 200 pixels, and we lose like 30% of the image. And we also like lose any interesting information that would have been like on the boundaries of the image. So let's consider like an example of like CCTV footage, and let's say there's like a suspect on like the borders of the footage. And then if we are losing, say like 30% of the image, that does not give us like a big chance to like find the person or like detect the face of the person. So we use padding to solve this issue. So what we do is we add extra pixels that are set to 0 around the boundary of the input image, which increases the effective size of the image. So if you look at the image on the left, there's a row and like columns of like zeros on the boundary. So that's what we do for like padding. And then in the video, we can also like see they have like the dotted lines around the blue box that shows padding. And then yeah. So I guess on the image, it initially starts with a 3 by 3 input, but then we increase the size to 5 by 5 by adding the zeros, and then our output increases to a 4 by 4 matrix. And then now let's talk about strive. So when computing the cross correlation, so like when we multiply input times kernel equals output, we start with the convolution window at the upper left corner, and then we slide it over all the locations, both down and to the right. But sometimes, either for like computational efficiency or because we want to downsample, we move our window more than one element at a time, skipping the intermediate locations. So we refer to the number of rows and columns traversed per slide as the stride. So far, we've only used strides of one, both for height and the width. So the video, it shows what a stride of two is. So instead of shifting the window by one square, we shift like the window by two squares each time. And if you want to like explore this further on your own, you can try it with the image and like the values on the left. Okay, so now let's talk about pooling. So pooling layers, they serve two purposes. The first is to mitigate the sensitivity of convolutional layers to location, and the second is to spatially downsample the representations. So what pooling operators are is that they consist of a fixed shape window that is slid over all regions in the input according to the stride, and we compute a single output for each location traversed by the window. So, and the pooling layer contains no parameters, so there is no kernel. And so what it does is the shaded blue region in the input, um, we either typically calculate the maximum or the average value of the elements in the window. So over here, if we want to do max pooling, we would just get the max of the elements in the blue box. That would be 4. And that's why you see in the output there's 4 for that mapping. Um, Yeah, so the next window would be moving it one to the right. So that would be 1, 2, 4, 5, and the max value there would be 5. So let us now take a look at the code for this. So here we implement what I just talked about. So we do in the output, we calculate the max of the input subtensor, or if we want to do the average pooling, we calculate the mean. So run this. And then we can once again just take an example of the input that I showed earlier to see if we're getting the right result. So here we get 4 and 5, which I just talked about earlier. So you can see that. And we can also experiment with the average pooling layer where we calculate the average values in the input subtensor. So do we have any questions so far? Is everything good? Okay. Okay, so let me introduce ResNet. So if you look at the graphs, we can see that the 20-layer CNN, it performs better on training and testing the data sets rather than the 56-layer CNN architecture. So if you look at the first graph, the training error for the 56-layer is higher than the training error for the 20-layer. And then similarly for the test, it is also higher than the 20-layer CNN. So the conclusion here was that the higher error for the 56 layer was being caused by a vanishing gradient, which is when the gradient becomes 0 when we increase the number of layers. So as we have a larger number of layers and as we keep iterating, the gradient keeps going closer to 0. But then we also do want to have more depth so that if we have more layers in neural networks, it allows the model to learn more complex features and representations from the input data. So ResNet was introduced to solve this problem of the vanishing gradient. So let me talk about the ResNet architecture. So in this network, we use a technique that's called skip connections. The skip connection connects activations of a layer to further layers by skipping a bunch of layers in between. And this forms like what is called a residual block. And ResNets are made by stacking these residual blocks together. And the benefit of including the skip link is that when we perform regularization, we'll skip any layer that degrades the architecture performance. So as a result, training like an extremely deep neural network is possible without encountering any issues with like vanishing gradients. And then let's see. And then yeah.
Can you explain that part again? How vanishing gradients are left with resonant.
Could you repeat that? I couldn't hear you.
How does resonant avoid vanishing gradients? Can you explain that part again?
Yeah, so say for example, there were like no skip connections and like all of these were just like regular like layers. So if you keep iterating through each layer, like as you get to the end, your gradient goes close to zero. But if you skip them, you're only like you're reducing the gradient like a fewer number of times because you're skipping like a bunch of layers.
How do you
So
choose to
it's-
skip the layers?
Do you have a whiteboard marker?
might be over here. It might sound like a bound, but
I can fetch you one if that helps.
no. I think it'd be easier if I draw it out, so I'll just wait for Tina to bring the marker.
We can go over my question after the workshop. We don't want to hold it.
I think we have enough time. We have 30 more minutes, so I think it's fine. Okay. Maybe just have like a bunch of layers. So say like we just have like 50 of these. And then if we're like calculating the gradient and we keep going, if we have like so many, at some point it becomes zero, and that's like the vanishing gradient problem.
Yeah.
But if we're like skipping, we're just going like this. So we skip like 5, I guess, and like 10 or like however many. So we aren't like, I guess we aren't like minimizing it so as much as it would have been when there's like 50 layers. That's why you don't end up with like a zero at the end.
But like, what I'm trying to understand is like, is there like a criteria for like which layers is supposed to be skipped and when you're supposed to skip a layer?
So the residual block skips every 4 layers by default. So we just chain residual blocks, and each residual block skips 4 layers. So it's like big architecture. The architecture itself is just every 4 layers, create a skip connection with the output from 4 layers before.
In the back propagation. Or like,
Even in forward inference.
like, what is the point of having the four layers skipped in?
Well, it's
The random.
when we skip it, it's creating a or like adding the previous layer with the current one. So even the 4 layers changes that they made, that is also part of the final output. We just added with the previous
I see.
the residual outputs in order to make sure that previous information is not discarded, while the new information that is obtained by processing just through the CNN weights
Yeah.
are also retained.
So they're, sorry.
So it's not like maybe if you have, say, skip connections and there are 10 skip connections,
Yeah.
it's not equivalent to a 10-layer CNN.
Yeah.
It has in the same depth as a 10-layer CNN, so you know you will not have a vanishing gradient, and at the same time you will have capacity to process very complex features because you also have the 50-layer CNN that's there.
So the weights of those 4 layers won't affect the weights of the next layers. Is
Uh,
that why?
It does, but the representation, it kind of disappears. So like it's like say you're going down a rabbit hole, right? Just exploring something within a subject, right? You research it for hours and hours and hours and use the high level of it, and then you go back, read the high level, and things start to make sense.
Yeah.
That is kind of what is happening over here, where you are exploring a very specific feature, right? At least theoretically, the understanding is with a deeper neural network, you explore a very specific feature that has very high complexity. However, you lose the breadth of what you are actually looking at, the original image, as an example. So you add the previous representation to this new process representation, so you have both high level and low level view of what you are trying to analyze. That helps the model perform better.
But then if these layers are skipped, they even in back propagation, they're skipped, but their weights are never changed, right?
So,
they're not being like,
by skip connection, it means more like a bypass. So like a highway, considered like information processing highway.
Okay.
So the information, say, from this layer is included in the input for this layer. So it gets this input as well as this input.
yeah.
So all of the
Oh,
information
so
is
the
probably.
previous- okay, I see.
Yeah, so both the aspects of it are included.
I see. So skip doesn't mean like they're making.
It doesn't mean it is ignoring it,
Okay.
it means it is considering other thing in addition to this.
Okay, I understand.
Yeah.
Okay, so just a quick overview of transfer learning. So this is a technique where a model that is trained on one task is reused or like adapted as a starting point for a different but also related task. And so instead of training a model from scratch, transfer learning uses the knowledge gained from solving one problem to tackle a new problem. So the intuition behind transfer learning for image classification is that if a model is trained on like a large and general enough data set, that model will effectively serve as a generic model of the visual world. So you can then take advantage of the learned feature maps without having to start from scratch by training a large model on a large data set. And there are generally two main approaches to transfer learning. So the first one is feature extraction. So here we use the representations learned by a previous network to extract meaningful features from new samples. So we simply add a new classifier, which will be trained from scratch on top of the pre-trained model so that you can repurpose the feature maps that are learned previously for the data set. And then the second approach is fine tuning, which is where you unfreeze a few of the top layers of a frozen model base and jointly train both the newly added classifier layers and the last layers of the base model. So this allows us to fine tune the higher order feature representations in the base model in order to make them more relevant for a specific task. So we can go back to the code. I will share another Colab notebook, and we can explore that further in through the code. Give me one. second here. Yeah, I sent another link, so let me know if everyone has access to that. So I'm just gonna like quickly explain because a lot of this is just like set up over here, and this does take like a long time to run. So I'm just gonna so I'll also send the link to this. I also just sent the link to the code for this portion, so if you want to take a look at that, you can. So what we're just doing here is like cloning the repository and then installing the requirements. And then after that's done, we'll just like change the directories and then run a script and then we can run the training. But this takes like a really long time. I think it might take like over 30 minutes. So I'm not gonna like run the whole thing and have the output here. However, if you are interested in like learning how to make it faster, we're gonna have another workshop on March 3rd, which will show how to like run these like computationally intensive stuff on Scholar, which will be a lot faster than trying to run it on whatever GPU Colab gave us here. So this is gonna take a long time, so I'm not gonna wait for this, but I'll just go into the code for here. Okay. So if we look at these lines over here, so here we're just like initializing the ResNet. So we do ResNet 50, and then we have this constant that's called pre-trained. So if we want to set it to true, it's going to load, it's going to like initialize a pre-trained ResNet model. But if we set it to false, it'll just not do that, I guess. So if you go here and you can go to cons.py, so this is where you can change any of the hyperparameters or stuff that you want. So if you want to like run it for fewer like epochs, you can edit that. Or if you want to yeah, so if you want to change this and see like the outputs, you can also do that. So what's going to happen here is basically if you use the pre-trained model, you would get a better, you'd get like a lower loss, versus if you use like a model that's not pre-trained, you get a higher loss. So later when you guys have time, you can look into that. But we go back here. Okay. So we initialize it over here and then we run the training loop like over here below. So we do like we calculate the gradients, back propagation, and then like update them. And then, yeah, so that's what we do over here. Yeah.
Can you talk a little bit more about how you set up the architecture with the pre-trained weights? Like just discuss lines or like the step model function?
The get model. Um, what exactly do you want me to explain here?
Well, how you, I mean, what exactly is happening, I guess? Why are we setting FC and I don't know, how do we go from ResNet 50 to our own custom model with the pre-trained weights? Well, we're initializing ResNet 50. Then within the weight section, we specify we want the default ImageNet trained weights. That's the original architecture. That gives us ResNet 50. But then after that, we want to remove the last layer because the last layer is for ImageNet classification, not our specific task. We want
So
to
that's one.
specifically tune it to the data set for animal classification. So there are 10 classes for animals, which is why we have a lazy linear layer, which just takes the flattened output, passes it to a final linear or like a dense layer with 10 classes or 10 outputs for 10 classes, and then softmax activation for probability distribution over that result. And then that is the new model which we fine-tuned because the last layer still has randomized weights. Everything before that though is image net frequency.
What is crazy linear? So just like linear.
Yeah, so usually we define linear where we have the input neurons as well as the output neurons. Lazy linear, it infers the input neurons by whatever is there before that.
Oh, right, so you don't have to put in the.
Yeah, so instead of saying, say, input 10, 5, and then 5, 15, you would just do 10, you would just do input, 5, and then 10,
Okay.
15 like that.
Oh,
Okay. Um, yeah. So here we're comparing two cases where one is like the pre-trained model and one is not the pre-trained model. So here we can look at the parameters. One is true and the other is false. So if we go down here, we can see the difference in the loss. So the pre-trained model has a way lower loss than the one that just used at the default weights. So yeah, I think that is all that I have. Did I not put in the thank you slide? Okay, I forgot to put in the thank you slide, but that is all I have, yeah.